A rule of the universe is about to break, not slowly, not subtly, completely. Two particles are created together, in the same place, in the same moment. Then they are separated. One travels across the galaxy, the other stays behind, light years apart, farther than any signal could travel in time, farther than any wire could stretch, and then one of them is measured. Instantly, the other one responds. No delay, no message crossing space, no time for light to move between them. The reaction is immediate, as if distance does not exist, as if space itself has no authority. How can something here affect something there? Instantly. This should be impossible. Every law we trust says information needs time. Even light, the fastest thing in existence, takes time to move. Yet in the microscopic world, nature seems to ignore that limit. This is not science fiction. This is not theory without proof. This has been tested again and again in real laboratories under strict conditions. The results forced physicists to accept a conclusion that once sounded absurd. The universe allows distant things to remain deeply connected. In this video, you will learn what that connection really is. You will understand why classical physics cannot explain it. You will see how decades of debate, bold mathematics, and precise experiments slowly confirm that this strange link is real. You will discover why one of the greatest minds in physics, Albert Einstein, refused to accept it and called it spooky action at a distance. You will learn how a quiet equation proposed by John Bell changed the debate forever and forced reality to choose between locality and completeness. And you will hear about the experiments led by Alain Aspect that tested nature itself and showed that the universe does not behave the way common sense demands. By the end, you will not only understand what quantum entanglement is, you will see why it challenges the very idea of separation, why it suggests that distance might not be as fundamental as we think, why modern technologies like quantum cryptography and quantum computers depend on this strange bond, and why this phenomenon hints at a deeper layer of reality where objects are not isolated pieces but parts of one connected system. This is not just a story about particles, it is a story about how science confronted an uncomfortable truth and survived it. Early physicists believed hidden variables might exist, secret instructions carried by particles from the start. If that were true, the universe would remain predictable and local. But when experiments violated Bell's inequality, the hope for simple hidden explanations began to collapse. The data did not bend. The universe chose non-local correlations. Even more surprising, entanglement does not allow faster-than-light communication. No usable signal is sent. No message is transferred in a way that breaks relativity. The connection is real, yet it cannot be used to transmit information in the normal sense. That subtle detail is one of the most misunderstood aspects of quantum physics. The link is instant, but it does not let us cheat the cosmic speed limit. That tension between instant correlation and no communication is where the mystery becomes deeper, not smaller. Stay until the end, because the final insight is not about particles at all. It is about how we define reality. It is about whether space truly separates things, or whether separation is simply how our senses interpret a deeper unity. The conclusion may change the way you think about connection itself. It may challenge the idea that objects are independent. It may even suggest that the fabric of the universe is woven from relationships, rather than isolated points. Every major breakthrough in physics forced humanity to let go of a comfortable belief. The Earth was not the center. Time was not absolute. Matter was not solid in the way it appears. Now entanglement asks us to consider another shift. Distance may not fully define independence. That shift is uncomfortable. It resists intuition, but the evidence stands. In the next few minutes, we will move carefully from the basic principles of motion and information to the quantum rules that break them. Step by step, clear and simple, no complicated equations, just the essential ideas. By the end, the question will return in a new form. How can distant things stay connected? Or perhaps the deeper question is whether they were ever truly distant to begin with. Welcome to Feynman's chalkboard, where we explore the universe one idea at a time. If you are curious about the hidden structure of reality and want to understand the science shaping our future, subscribe now and join us as we look beyond the surface of the world we think we know. Distance, in the world we see every day, follows strict rules. If you want to send a message to someone across the room, your voice must travel through the air. If you send a signal to another city, it moves through wires or satellites. Nothing simply appears somewhere else without crossing the space in between. Information takes time to travel. That is one of the most basic principles of physics. Even the fastest thing we know, light, has a limit. It moves at about 300,000 kilometers per second. That speed feels infinite to us, but it is not infinite. Light from the sun takes about 8 minutes to reach Earth. Light from distant stars can take thousands or even millions of years to arrive. The universe has rules, and one of those rules is clear. No information can move faster than light. This rule protects cause and effect. First something happens, then its effect follows. Cause must come before effect. If that order breaks, logic breaks with it. Time would lose meaning. Distance would lose meaning. Physics would lose structure. This is why the idea of instant influence across space felt unacceptable to many scientists. Among them was Albert Einstein. He believed deeply in the consistency of nature. For him, the speed of light was not just a number, it was a boundary built into reality itself. When early quantum theory suggested that two distant particles could affect each other instantly, Einstein rejected it. He called it spooky action at a distance. The phrase was not praise, it was criticism. He felt that something was incomplete in the theory. He believed that there must be hidden details not yet discovered, hidden variables that secretly determined outcomes in advance. To Einstein, distance had to matter. Objects separated in space had to be independent unless something physically connected them. Nothing should travel faster than light. No effect should happen before a cause. Locality, the idea that objects are only influenced by their immediate surroundings, seemed essential. Yet as quantum mechanics developed, experiments began to suggest that nature did not fully obey this intuition. Tiny particles behaved in ways that ignored the neat boundaries of classical thinking. Instead of acting like separate pieces, they sometimes behaved like parts of a single system, even when far apart. This is where the core idea appears, not as fantasy, but as a measured phenomenon called quantum entanglement. When two particles interact in certain ways, they can become linked. The link is not like a rope. It is not a physical thread stretching between them. It is not a signal passing back and forth. It is deeper than that. Their properties become correlated. For example, imagine two particles created together with opposite spins. Spin is a quantum property, not exactly like spinning in everyday life, but similar enough to picture as orientation. If one particle is measured and found to have spin up, the other will be spin down. If one is down, the other is up. Before measurement, quantum theory says neither particle has a definite value. They exist in a combination of possibilities. Only when one is measured does a specific outcome appear, and at that same moment, the other particle's outcome is fixed as well, even if it is light years away, not connected by a wire, not connected by energy being sent through space, connected by information embedded in their shared quantum state. The instant one result becomes real, the other becomes real in a matching way. It does not matter if the particles are separated by meters or galaxies, the correlation holds. It is crucial to understand what this does not mean. It does not mean we can send messages faster than light. If you measure one particle, you cannot control the result. You cannot choose spin up or spin down at will. The outcome is random. Because it is random, you cannot encode information in it. Only when results from both sides are compared later do the correlations appear. So entanglement is not communication. It is correlation, deep, instant, unexplained by classical intuition. For decades, many physicists were uncomfortable with this. They wondered whether quantum theory was incomplete. Maybe the particles already carried instructions hidden inside them. Maybe when they were created, they agreed on what outcomes they would show later. If that were true, there would be no need for instant influence. Everything would have been decided in advance. This idea became known as hidden variables. It preserved locality, it preserved realism, the belief that physical properties exist before we measure them. But how could one test whether hidden variables were real, or just a comforting assumption? This is where John Bell entered the story. In the 1960s, he developed a powerful mathematical argument known as Bell's theorem. Bell showed that if hidden variables existed and obeyed locality, then certain statistical limits would always be respected in experiments. These limits are expressed as inequalities. They set boundaries on how strongly correlated distant measurements could be. Quantum mechanics predicted that under certain conditions, those limits would be violated. That meant nature itself could decide between local hidden variables and non-local quantum correlations. This was no longer philosophy, it became an experimental question. Physicists began designing tests. They created pairs of entangled particles and measured their properties at different angles and settings. If the results stayed within Bell's limits, hidden variables might survive. If the results crossed those limits, locality would be in trouble. In the early 1980s, Alain Aspect and his team performed one of the first convincing experiments. They measured entangled photons and changed the measurement settings rapidly while the photons were already in flight. The results violated Bell's inequality, matching quantum predictions. Many physicists were stunned. Still, some argued that loopholes remained. Maybe the detectors missed too many particles. Maybe subtle communication was possible through unnoticed channels. Over the next decades, technology improved. Experiments became more precise. Researchers worked to close every possible loophole. Eventually, advanced tests were performed in multiple laboratories around the world, including facilities connected to CERN. These experiments used high-efficiency detectors and ensured that measurement choices were made in ways that prevented hidden coordination. Again and again, Bell's inequality was violated. The universe refused to behave locally. Entanglement was not a mistake, not a trick of math. Reality itself allowed distant connection. This forces a deeper question. If no signal travels between the particles, what exactly is happening? Are the particles sending hidden messages in ways we do not yet understand? Or are they not truly separate objects in the first place? Quantum theory describes entangled particles as sharing a single combined state. Mathematically, they are one system, even when separated in space. Perhaps what we call two particles are simply two parts of a larger whole. In that view, the instant correlation is not information traveling, it is one system revealing consistent outcomes in different locations. Maybe distance is not fundamental at the deepest level. Maybe separation is something that appears only when we look from a classical perspective. On the quantum level, reality might be structured by relationships rather than by independent pieces. This idea reshapes how we think about space. We usually picture space as empty distance between objects. Empty space separates things, it keeps them apart. But entanglement suggests another possibility. Space may not fully define independence. 2 points far apart in space can still belong to a single quantum state. The link between them does not weaken with distance. It does not fade as they move apart. It simply exists as part of the structure of reality. That leads to a shift in perspective. Instead of imagining the universe as built from tiny separate blocks, we might think of it as woven from connections. Objects may be secondary, relationships may be primary. The properties of particles may not belong entirely to the particles themselves, but to the network of correlations between them. In this view, space is not only what separates, it is also what allows patterns to extend. The emptiness between objects may hide a deeper unity. Entanglement does not erase space, but it challenges the idea that space alone defines what can influence what. It shows that the universe is more subtle than classical pictures suggest. At the microscopic scale, the rules that guide everyday intuition give way to a structure where correlation outruns distance without breaking the speed of light. No signal exceeds that limit. Relativity remains intact. Yet locality, as once imagined, does not survive unchanged. The world at its foundation appears less like a collection of isolated parts and more like a web of connected events. The implications continue to unfold in modern research, from quantum communication to quantum computing, where entanglement is treated not as a puzzle but as a resource. Still, beneath the practical applications lies the deeper mystery. What is truly connected when two particles remain correlated across vast distances? Is it information, probability, or something even more fundamental? The question remains open, inviting us to reconsider what we mean by separation and what we mean by togetherness within the fabric of the universe. We began with a simple but unsettling question: how can distant things stay connected? At first, it sounded like a mistake in our understanding, a glitch in the equations, a problem waiting to be fixed. Distance should separate, space should divide, objects far apart should live independent lives. That is how the world appears to us. That is how classical physics trained us to think. Yet when we looked deeper, when we followed the experiments instead of our intuition, the picture began to change. Entangled particles do not ask for permission from distance. They do not wait for signals to cross the gap. They reveal outcomes together, instantly correlated, even when light itself would need years to travel between them. No visible bridge connects them. No message runs between them, and still the link remains. So we return to the question, but now it feels different. How can distant things stay connected? Perhaps the problem is not connection. Perhaps the problem is our idea of distance. Maybe what we call separation is only a surface feature of reality. Maybe at a deeper level, the universe is not built from isolated pieces scattered through empty space. Maybe it is built from relationships that stretch across space without weakening. Entanglement does not just challenge physics, it challenges perspective. It hints that what appears divided may share a hidden unity. When Albert Einstein resisted this idea, he defended a universe that made intuitive sense, a universe where locality preserved order. But experiments inspired by John Bell and carried out by scientists like Alain Aspect forced a different conclusion. Reality does not always follow the path of comfort. It follows the path of truth. And truth, in this case, tells us that the fabric of existence is more connected than we ever assumed. The deeper we look into reality, the less separate everything becomes. If this shifted the way you see the universe, if it made you pause and question the meaning of distance, then you are exactly where discovery begins. Subscribe to Feynman's chalkboard to continue exploring ideas that stretch the limits of understanding, like this video, so more curious minds can find it. Share it with someone who thinks the universe is simple. Because the closer we examine reality, the stranger and more connected it reveals itself to be.